Okay, so in the previous lecture, we introduced co-representations of compact quantum groups. Let's recall the definition. Suppose that we have a compact quantum group, and suppose that E is a finite dimensional vector space. By definition, a co-representation of our compact quantum group on E is an invertible element U in the tensor product of L of E and A, where L of E denotes the algebra of all linear operators on E, such that the following equality holds. So in this formula, we use the leg numbering notation, U12 and U13. So these are elements in the triple tensor product, L of E, tensor A, tensor A. So the left-hand side obviously belongs to this algebra, and U12 and U13 denote the canonical images of U in this algebra under the two natural embeddings. So the first natural embedding embeds the tensor product of L of E and A onto the first two factors here, and the second embedding, which takes U to U13, embeds this tensor product to the tensor product of the first and the third factors here. Okay, so that's our definition. And we have seen at the previous lecture that in the commutative case, that is in the case where A is the algebra of continuous functions on the compact group, co-representations correspond bijectively to continuous representations of the group on finite dimensional vector spaces. And also an important class consists of unitary co-representations. So if E is a finite dimensional Hilbert space, and if our element U is not just invertible but is unitary, then we say that U is a unitary co-representation. Okay, let's also recall that our element, actually each element U in our tensor product, L of E and A, corresponds bijectively to an element delta U, which is a linear operator from E to E tensor A. For the simple reason that these two vector spaces, this one and this one, are isomorphic for each finite dimensional vector space. So if we apply this canonical isomorphism to U, then we get delta U. And equivalently, the same element corresponds to an endomorphism, U tilde, of the free A module E tensor A. Again, because these two spaces, this one and this one, are canonically isomorphic. Okay, now to study co-representations, it's useful to interpret them as representations of the dual algebra way. So let's recall that the dual space of A star is actually a Banach algebra under convolution. And the convolution is defined as follows. If we have two linear functionals, two continuous linear functionals f and g on A, then their convolution f star g is defined by the following formula. So here delta is the co-multiplication, and f tensor g denotes the respective linear functional on the C-star tensor product of A by itself. Okay, now suppose that we have a co-representation. Suppose that U is a finite dimensional co-representation of our compact quantum group on E. And let's define a map pi U from A star to L of E, to the algebra of operators on E, by the following formula. So U sits in this tensor product. So after we apply one tensor f to U, and here one denotes the identity map of L of E, the resulting element will belong to L of E. And so we get a map pi U from A star to L of E, which is obviously linear. It turns out that pi U is a representation. So we have the following proposition. Pi U is a representation of A star. That is, it's just an algebra homomorphism from A star to L of E. Well, okay, so to prove this result, we need a simple lemma. Lemma and an exercise at the same time. So we have the following identity. For each pair of elements U and V in our tensor product of L of E by A, and for each pair of linear functionals f and g on A, we have the following identity: one tensor f tensor g applied to the product U12 V13 equals the product of two operators, one tensor f of U and one tensor g applied to V. The proof is absolutely straightforward. So you just, to check this formula, it's enough to prove this in the case where U and V are elementary tensors. And if they are elementary tensors, then the proof is just a straightforward computation. Very easy. Okay, now we can prove the proposition. So we take f and g in A star, and we calculate, we apply pi u to their convolution. So by definition, this is one tensor fg applied to u. So we substitute here the definition of the convolution. So this will be one tensor f tensor g composed with delta and applied to u. So we can equivalently write this element as follows: one tensor f tensor g composed with one tensor delta and apply it to U. Now, since U is a co-representation, we have the following. So one tensor delta applied to U is the product U12, U13. And now we apply our lemma. We apply our lemma and we see that this is nothing but one tensor F of U multiplied by one tensor G of U, which is exactly pi U of F pi U of G. And that's it. So we see that pi U is an algebra homomorphism. That is, pi U is a representation of a star on the same space E. Okay, so we see that each finite dimensional co-representation of A induces a representation of the dual algebra. Our next goal is to show that this correspondence is actually a fully faithful functor. In other words, we have the following result. Next proposition. Suppose that U and V are two finite dimensional co-representations of A, of our compact quantum group. Then we have the following equality. In other words, a linear map between the respective co-representation spaces is a morphism of co-representations, even only if it is a morphism of the respective representations, pi U and pi V. Okay, to prove this proposition, we again need a couple of simple lemmas. Lemma exercise 1. Which actually gives us an equivalent, but different but equivalent form for pi U of F. Namely, for each linear functional f on A, and for each element U in tensor product of L of E and A, we have the following identity. So this is the operator which appears in the definition of pi U. And the same operator can be written as follows. So clearly both sides are operators on E, because, well, let's write this down. The right-hand side, what is the right-hand side? Delta E acts from E to E tensor A. And after we apply one tensor F and compose them, we get a map from E to itself. So both sides of these of this formula are linear operators on E, and we claim that they are equal to each other. And again, the proof is delta E. Not delta. I denote this map by delta U, if I'm not mistaken. Let's look once again. Yes, this is delta U. Okay, so this is a straightforward computation. Again, it's by linearity, it's enough to prove this formula in the case where U is an elementary tensor. And in this case, the proof is straightforward. Okay, and now lemma 2, lemma exercise 2. Suppose that X is a vector space and Y is an Orient space. then for each non-zero element, say z, in their algebraic tensor product, there is a bounded linear functional f on y such that one tensor f, here one is the identity map of x, doesn't vanish at z. In other words, linear maps, slice maps of this form separate the points of the algebraic tensor product. Well, again, the proof is a standard combination of standard linear algebra and the Hahn-Banach theorem. Okay, now let's prove our proposition. So let's take a linear map T from E to F. Here I assume that E is the space, the co-representation space for U, and F is the co-representation space for V. So U is the co-representation of A on E, and V is a co-representation on F. So we see that we want to show that T is a morphism from U to V, if and only if T is a morphism from pi U to pi V. So let's recall the definition of a morphism between co-representations. Actually, we have seen there are several equivalent definitions for morphisms of co-representations. At this point, it will be more convenient to use the definition given in terms of the respective delta maps, delta U and delta V. So this is equivalent to the following. T tensor 1 composed with delta U equals delta V composed with T. So at the previous lecture, we wrote this formula in the form of a suitable commutative diagram. This is one of the equivalent definitions of a morphism between co-representations. Okay, so now both sides of this formula are maps with values in the tensor product of V of F and A, and we can now apply lemma 2 to the tensor product of F and A. Such slice maps separate the points of the tensor product, and so this is equivalent to the following. For each bounded linear functional f on A, one tensor f applied to composed with T tensor 1 and composed with delta U equals one tensor f composed with delta V and composed with T. Okay, now what is the right-hand side here? We apply now lemma 1. So we look here, and we see that the right-hand side here is the composition of pi V of F and T by lemma 1. And the left-hand side can be written in the following way. First of all, we observed that one tensor F composed with T tensor 1 is equal to T composed with one tensor F. So this is the identity map of E. And applying lemma 1 again, we see that this is nothing but T composed with pi U of F. So we see that T is a morphism of co-representations if and only if this operator equals this operator. But this is precisely the definition of a morphism between representations. So this means exactly that T is a morphism from pi u to pi v. And this completes the proof. Okay. Okay, let's now discuss invariant subspaces for co-representations. We have the following proposition. Again, suppose that U is a finite dimensional co-representation of our compact quantum group, A delta, on a finite dimensional vector space E. Also, suppose that F is a vector subspace of E, and let P be any projection of E onto F. Of course, there are many such projections, so we can take any of them. Then the following conditions are equivalent. Condition 1, we have the following equality. P tensor 1, U, P tensor 1 equals U, P tensor 1. And this identity holds in L of E tensor A. Property 2, U tilde, so we recall that U tilde is an endomorphism of E tensor A corresponding to U. So let's look at this definition once again. So U tilde acts from E tensor A to itself, and it corresponds bijectively to the element U under the canonical isomorphism between this algebra and this algebra. So property 2 says that U tilde takes F tensor A to itself. And property 3, delta U, which acts from E to E tensor A, takes F to F tensor A. Well, the proof is very easy. First of all, let's observe the following. We observe that if you take the tensor product of P and the identity map of A, then this operator is a projection of E tensor A onto F tensor A. Simply because P projects E onto F. Now, condition 1. First of all, we write condition 1 in a slightly different way. So we replace L of E tensor A by the isomorphic algebra of endomorphisms of E tensor A, and we get the following equality. So U will be replaced by U tilde. And this is an equality in the algebra of endomorphisms of the free module E tensor A. Okay, now since P tensor 1 is the projection onto F tensor A, this means that this equality means that that these two operators, P tensor 1 U tilde and U tilde, coincide on the image of P tensor 1. But the image of P tensor 1 is F tensor A. So this means that P tensor 1 U tilde equals U tilde on F tensor A. And again, since P tensor 1 projects E tensor A onto F tensor A, we see that this means exactly that condition 2 holds. That is, U tilde takes F tensor A to itself. Okay, so this shows that 1 and 2 are equivalent. And the equivalence between 2 and 3 readily follows from the explicit relation between U tilde and delta U. Namely, delta U takes an arbitrary element, say X, F to U tilde applied to X tensor 1. And U tilde takes X tensor A, takes each elementary tensor to delta U of X multiplied by A. So this is the explicit formula which gives us correspondence, bijective correspondence between U tilde and delta U. And this readily follows, these formulas readily imply that 2 and 3 are equivalent, because if U tilde takes F tensor A to itself, then this formula shows that delta U takes F to F tensor A. And similarly, if delta takes F to F tensor A, if this holds, then this formula shows that U tilde takes F tensor A to itself. Okay, so we see that conditions 1, 2, and 3 are equivalent. And if they are satisfied, then we say that F is a U-invariant subspace. So by definition, F is a U-invariant subspace if U satisfies any of the above conditions. Any of the above conditions, and since they're equivalent, hence it satisfies all of the above conditions. Okay, well, of course, this notion, the notion of a U-invariant subspace, comes from group representations. So let's look at the commutative example. Let's look at the commutative case. Suppose that A is the algebra of continuous functions on a compact group. So our element U, our co-representation U, is actually a representation of U on E, that is, map from G to GL of E. Now, delta U acts from E to E tensor A, and we identify E tensor A with the space of continuous E-valued functions on G. And explicitly, delta U is given by the following formula. So this was discussed at the previous lecture. It takes each vector V to the function given by the following formula. We simply apply to V the operator U of X for each X in G. So we see that our subspace F is U-invariant. So one of the conditions, one of the equivalent conditions, is that delta U takes F to F tensor A, which is the same as the space of F-valued continuous functions on G. And if you now look again at the explicit formula for delta U, we see that this means exactly that for each element v in f, the resulting function takes g to f. So in other words, this element belongs to the same subspace f. So this means that u of x takes f to itself for each x in G. That is, f is invariant with respect to u in the sense of representation theory. Okay, now let's observe that in fact this inclusion is inequality, for the simple reason that we can replace here x by x inverse. And this equality leads directly to the notion of subrepresentation. So just for each element x in G, we take the operator u of x and restrict it to f. And by the above formula, by this formula, it follows that u of x is an invertible operator on f. And so we actually have a representation on f. And now a natural question is there a quantum analog of the notion of a subrepresentation? So in other words, you have a co-representation U and an invariant, a U-invariant subspace F. Can we construct a co-representation on F? It turns out that the answer is yes. But this is not entirely obvious. The reason is that if we look again at the definition of an invariant subspace, for example, let's look at condition 2. By assumption, U is invertible, or currently U tilde is invertible. But in general, if we have this inclusion, it is not immediate at all that this inclusion is an equality. Or currently, it is not obvious that the restriction of U tilde to F tensor A is still invertible. And so at this point, we cannot claim that we have a subrepresentation on F. It turns out that the answer is yes, but we will see this only at the end of today's lecture. Okay. Our next result again, it involves the representation of the dual algebra. I claim that a subspace f of E is U invariant, even only if f is pi U invariant, which is quite useful. Well, the proof is more or less straightforward computation. So before we do this computation, let's observe the following. If you take an arbitrary continuous linear functional f on A and look at the map, which appears in the definition of pi U, so this map acts from L of E tensor A to L of E. So this map L of E. So this map is an L of E bimodal morphism. Actually, we have already used this fact when we discussed slice maps. Okay, now let's prove our proposition. So we take a projection. Let P be a projection of E onto F. And we observe that F is pi U invariant if and only if for each F in A star, we have the following formula. P pi U of F P. Well, maybe it's better to write this in a separate line. P pi U of F P equals pi U of F P. So it's more or less immediate that this quality means exactly that that pi U of F takes a big F to itself. That is, F is a pi U invariant subspace. Okay, now let's write the right-hand side in a slightly different way. So first of all, we substitute pi U of F here, and this will be 1 tensor F applied to U, and then multiplied by P. And now we use the fact that 1 tensor F, the slice map, is right L of E modulo morphism. So we write this formula in the following way: 1 tensor F applied to the product of U and P tensor 1. The right action of P on the tensor product is given by the multiplication, by the right multiplication with P tensor 1. Okay, so this is the right-hand side of our equality, and similarly the left-hand side can be written in the following way. This will be 1 tensor F applied to P tensor 1 U P tensor 1. Okay, so we see that F is pi U invariant if and only if this element, this operator, equals this operator, and this holds for each F in A star. And now we apply one of our previous lemmas, which states that slice maps of this form, 1 tensor F, separate the points in the tensor product. And so these two elements are the same for each F, if and only if this element is equal to this element. Pi tensor 1 U pi tensor 1 equals U pi tensor 1. This follows from one of our previous lemmas. But this identity means exactly that that F is U invariant. And this completes the proof. So we see that F is U invariant if and only if it is pi U invariant. Okay, now we naturally come to the notion of an irreducible co-representation. So again, suppose that we have a finite dimensional co-representation U of our compact quantum group A delta on a finite dimensional vector space E. And we say that U is irreducible if the zero subspace and E itself are the only invariant subspaces. The only U-invariant subspaces of E. So the definition is quite natural, and it's very similar to the notion of an irreducible representation of a group or an associative algebra. So now, as a corollary of the above result, we see that U is irreducible, even only if the respective representation of the dual algebra, the representation pi U, is irreducible. This follows from the previous result, which states that a subspace is U-invariant if and only if it is pi U-invariant. And as another corollary, we get a co-representation version of Schur's lemma. Suppose that we have two finite dimensional irreducible co-representations, U and V. Then the following results hold. First of all, if U and V are not isomorphic, then the only morphism from U to V is 0. Second, if they are isomorphic, then the space of morphisms from U to V is one-dimensional. And as an important special case, the algebra of endomorphisms of U looks as follows. So it consists of operators which are multiples of the identity operator. And to prove this result, we simply apply the classical Schur's lemma to the representation pi U. By classical Schur's lemma, I mean Schur's lemma for finite dimensional representations of associative algebras. And that's it. So since morphisms of co-representations bijectively correspond to morphisms of the respective representations, we get our result. Okay, now we come to the following important theorem. And this will be our first, this will be the first place where we'll use the Haar measure, the Haar state. Briefly, the result states that a finite dimensional co-representation of a compact quantum group is unitarizable. More exactly, this means the following. If we have a finite dimensional co-representation, say V, is a finite dimensional co-representation of our compact quantum group A delta on a finite dimensional Hilbert space, finite dimensional Hilbert space H, then there exists a unitary co-representation, U, of A on the same Hilbert space such that U and V are isomorphic. Okay, so this is our result. And again, as before, the proof will be based on a couple of simple computational lemmas. Lemma 1, lemma exercise 1. Suppose that we have two unital algebras A and B. So this is a pure algebraic lemma. It holds for arbitrary unital algebras A and B. And suppose that we have a linear functional H on A, linear functional, and we have three elements X, Y, and Z in the tensor product B tensor A tensor A. Then the following equality holds. 1 tensor H tensor 1 applied to x1 3, y1 2, and z1 3, and this is equal to the product of x. Next we have 1 tensor H applied to 1, and tensor the identity of our algebra A, and then multiplied by z. I hope this is correct. This is absolutely impossible to remember, so I sometimes look into my notes, if you don't mind. Yes, this is correct. Okay, the proof again is a straightforward computation. So again, by linearity, it's enough to prove the formula in the case where x, y, and z are elementary tensors. We'll just substitute them into both sides of the formula and calculate. That's it. Well, this is very easy. And lemma 2, which is also quite straightforward. Lemma exercise 2. Suppose that we have a finite dimensional co-representation of a compact quantum group. So A delta is a compact quantum group, and V is a finite dimensional co-representation of A. And suppose we have an invertible linear operator from E to another finite dimensional vector space F. And let's consider the following element. Let's denote by U the product T tensor 1, V, T inverse tensor 1. So this is an element in L of F tensor A. And I claim that U is again a co-representation of A on F. Well, again, the proof is straightforward. So obviously this element is invertible because it is the product of three invertible elements, three invertible operators. And after we do a little calculation, we see that U satisfies the same relation. So 1 tensor delta applied to U is the product U12, U13. So if V satisfies this condition, then U also satisfies the same condition. So this is a simple, useful way of producing new co-representations. And of course, And of course, if we look again at the definition of U, we conclude that T becomes an isomorphism. T is an isomorphism from V to U. Simply because this equality is actually one of the equivalent definitions of an isomorphism of co-representations. Okay, let's now prove our result, our theorem. So we want to show that there is another co-representation which is unitary and which acts on the same Hilbert space and which is isomorphic to U. So we'll construct U with the help of lemma 2. So first of all, we construct a suitable operator T. And this is exactly the place where we use the higher measure. We define an operator T as follows. In some sense, this is a quantum analog of the standard averaging procedure, which is known in the theory of compact groups. So we, if V is, if we are in the commutative case, then V is a representation, an operator valued function, and we just average this function over the group. That is, we take the integral, and we get a U operator T. So this is an operator on E. So what can I say about this operator? Well, first of all, V star V is positive. V star V is positive, and it is invertible because V is invertible. And so we conclude that V star V satisfies the following inequality. This is the identity in the tensor product of B of H and H for some positive epsilon. This means precisely that V star V is positive and invertible. Now we apply one tensor H, and well, H is a positive function, it's a state, so it preserves the order relation. So this implies that one tensor H also preserves the order relation. And also, since H is a state, it takes the identity to the identity. And so the same is true for one tensor H. So after we apply one tensor H, we conclude that the operator T satisfies a similar inequality. And in particular, this implies that T is invertible. Okay, so we now define a new co-representation. We let U denote the following element. We take the square root of T, tensor 1, V, the inverse of the square root, tensor 1. So this is an element in oh, sorry, I write LOV, but actually is H here. Our representation space is H, and instead of L, I write script V in order to emphasize that this is the C star algebra of all bounded operators on H. Okay, so U is an element in the tensor product of B of H and A. And lemma 2 implies that U is a co-representation. U is a co-representation of A on H, and U is isomorphic to V. So now, to complete the proof, we have to show that U is unitary. Well, why is it unitary? Let's calculate U star U. We want to show that U star U equals 1. Since U is invertible, this will mean exactly that U is unitary. So what is U star U? Well, U star is, what is U star? This is T 1/2 tensor 1 tensor V star. This is U star, and we multiply U star by U. Oh no, is that correct? No, this is not correct, because the U star, we first take the adjoint of this, but this is self-adjoint. So this will be t to the power minus 1/2 here, and t to the power 1/2 here. Okay, so this is U star, and then we multiply it by U. So this is the product of U star and U. So we see that U is unitary, that is U star U equals 1, even only the following equality holds. So this should be equal to 1, and we multiply it on both sides by this operator. So after we do it, in the left-hand side, we will have V star T tensor 1 V, and in the right-hand side, we will get T tensor 1. So we have to show that this equality holds. This will mean exactly that U is unitary. Okay. Well, why is it so? So to show that this is indeed the case, we do a little trick. So since V is a co-representation, V is a co-representation, we have the following equality: 1 tensor delta applied to V star V is equal to the following product. This is V1 3 star, V1 2 star, V1 2, V1 3. This follows from the fact that 1 tensor delta is a star homomorphism, and it takes V to V1 2, V1 3. So since it's a star homomorphism, it takes V star V to this element. Okay, and now we apply the following operator to this equality. So this equality holds in B of H tensor A tensor A. And we apply the following operator to both sides of this formula. 1 tensor H tensor 1. And we get the following. So the left-hand side looks as follows: 1 tensor H tensor 1, 1 tensor delta applied to V star V. So what is this? The composition of H tensor 1 and delta, since H is her state, it is nothing but eta H, where eta is the unit map. And we apply it to V star V. Well, now we write this in the following way: 1 tensor eta, 1 tensor H applied to V star V. 1 tensor H applied to V star V is our operator T. And after we apply 1 tensor eta, we get T tensor 1. Okay, so this is the result of applying this operator to the left-hand side of this equality. And now let's apply the same operator to the right-hand side of the same equality. 1 tensor H tensor 1 applied to V13 star, V12 star, V12, V13. So what is this? Well, this element in the middle is nothing but V star V12. So we can now apply lemma 1. Let's look at lemma 1. So we're exactly in this situation. So applying this formula, we get the following. So this is V star multiplied by 1 tensor H applied to V star V tensored by 1 and multiplied by V. This follows from lemma 1. And finally, we see that this element here is nothing but T. So this is equal to V star T tensor 1 V. And that's it. So we see that this element is equal to this element. So this implies that T tensor 1 equals the following element. But we have already observed, let's now look here. We have already observed that this equality means precisely that U is unitary. So let's denote the formula somehow, for example, as star. So now formula star implies that U is unitary. And this completes the proof. So each finite dimensional representation is unitarizable. It's interesting to compare this proof with the proof of the respective classical result about representations of compact groups. So a little remark. Well, it's a standard fact that if G is a compact group, and the pi is a finite dimensional representation of G on a finite dimensional Hilbert space H, then pi is isomorphic to a unitary representation. And usually the most standard proof looks as follows. We define a U inner product on the same Hilbert space, on the same space H. We define a new inner product. We just average the old inner product as follows. It's denoted by inner product with so the subscript G. So we integrate the following expression over G with respect to the normalized Haar measure P of X U and P of X V. And then a simple computation shows that P is unitary with respect to this new inner product. So basically, the standard proof does the following. So we keep the same representation pi, but we change the inner product on H. This is not entirely similar to our proof, because in our proof, we keep the same inner product, but we construct a new co-representation. So this looks a little bit different. But in fact, this difference is inessential. So I recommend you to do the following exercise. Show that if A is the algebra of continuous functions on a compact group, then our proof and the standard proof are, in some sense, essentially the same. So in particular, I suggest you to understand what I mean by essentially the same. Formally, they are different, but they are they can be reduced to each other very easily. Okay. Okay, let's now apply this result to, first of all, let's write this result in a matrix form. So we get the following corollary, corollary 1. Suppose that A is a compact quantum group, and suppose that U is a matrix co-representation. So let's recall that matrix co-representation is a square n by n matrix with entries in A, which satisfies some natural condition. So delta applied to the matrix elements is given by a very nice formula. Well, let me write this down. Delta U of j, Uij, is the following sum. We have observed at the very end of the previous lecture that matrix co-representations bijectively correspond to co-representations after we fix an arbitrary basis in our co-representation space. Then there exists an invertible matrix T, an invertible complex n by n matrix T, such that the element T U T inverse is unitary. This result is just a matrix form of our previous theorem. And let's now apply this to compact matrix quantum groups. Corollary 2. Suppose that A, delta, and U is a compact matrix quantum group. So this means that A is a unital sister algebra and delta is a unital star homomorphism from A to A tensor A. And U is a certain matrix which is invertible such that the U transpose is also invertible, and delta takes U to the element given by this formula. So this is useful special. The compact matrix quantum groups form a useful special subclass of the class of all compact quantum groups. In particular, this class contains the quantum SU2 group by Voronovich, and also free quantum groups, which are defined in our last exercise sheet, which I hope is already on the website of the course. Okay, so suppose that we have a compact matrix quantum group. We have already observed that U is a co-representation, is a matrix co-representation. So by the previous corollary, there exists an invertible matrix T such that, let's denote this product by U prime. This is T inverse, and this matrix is unitary. And moreover, in this case, if we replace U by U prime, we still get a compact matrix quantum group. The proof is a simple exercise. Actually, we already know that we can find T such that this matrix is unitary. So the only step is to show what has to be proved is that if we replace U by U prime, then the axioms of compact matrix quantum group still hold. But this is very easy. This is simple computation. And in this situation, it's natural to identify these two compact matrix quantum groups. This is a standard convention. Identify A delta U with A delta U prime. This is quite natural because, well, the underlying compact quantum group is the same, and A and delta are the same. So we usually identify such compact matrix quantum groups. Okay, now we are ready to characterize commutative compact matrix quantum groups. So we have the following proposition. Suppose that A, delta, and U, this triple is a commutative compact matrix quantum group. We already know that in this case we can assume from the very beginning that U is unitary. And let G denote the maximal spectrum of A. So since A and delta is a compact quantum group, it follows that G is a compact group. I claim that the following holds. First of all, the map from G to the unitary group U of n, which takes each character chi away to the following unitary matrix. So we simply apply chi to each entry of the matrix U. And I claim that this map is a topological isomorphism of G onto a closed subgroup of the unitary group of U n. And second, if we look at the Gelfand isomorphism, we already know that this is an isomorphism of compact quantum groups. It takes A to C of G. So I claim that this isomorphism satisfies the following property. It takes the matrix entries of our matrix U, takes each Uij to the function on G, which takes each matrix X to the respective matrix entry Xij. Here we identify G with a subgroup in U of n by means of the embedding described in part 1. Again, the proof is a nice exercise for you. Actually, the proof is very similar to the proof of one of our earlier results, namely the proof of the universal property of the algebra of continuous functions on the SU2 group. If you use the same argument you will easily get the proof of this result. Let's now, in conclusion, combine this result with some facts from the theory of Lie groups. The first standard fact is that if G is a closed subgroup in the unitary group, then G is a compact Lie group in a natural way. In fact, each closed subgroup of a Lie group is a submanifold automatically. And so G is a closed subgroup and a closed submanifold in UN, so it's a compact Lie group. The second fact is, if we start with a compact Lie group, G is a compact Lie group, then G is topologically isomorphic to a closed subgroup of the unitary group. The closed subgroup of UN for some natural number n. This is a classical result in Lie group theory. And finally, fact 3 is that if we have two Lie groups, G and H, and a continuous group homomorphism F from G to H, continuous group homomorphism, then F is smooth automatically. Okay, if we now combine these facts with our previous result, we see that there is an equivalence of categories. The category of compact Lie groups, the dual of the category of compact Lie groups, is equivalent to the category of commutative compact matrix quantum groups. So the philosophy behind this result is that an arbitrary compact matrix quantum group can be interpreted as a compact quantum Lie group. So this point of view emphasizes the role of compact matrix quantum groups. Okay, so unfortunately our time is up, so I have to stop here. So if we had a little bit more time, say about 4 to 5 lectures, I think, we could prove the following results. First of all, if we speak about arbitrary unitary finite dimensional co-representations of compact quantum groups, it turns out that the orthogonal complement of an invariant subspace is also invariant. This is not obvious, but this is indeed true. And this follows from the fact that each finite dimensional co-representation of our compact quantum groups generates a very useful finite dimensional C-star algebra on the same Hilbert space. And a subspace in this space is invariant, is U-invariant, if and only if it is invariant with respect to this concrete C-star algebra. And this really implies that the orthogonal complement of an invariant subspace is also invariant. As a corollary, this implies that if we restrict an arbitrary co-representation to an invariant subspace, we again get a co-representation. So this was not obvious from the very beginning, but this is indeed true. And also, this result shows that each finite dimensional unitary co-representation is isomorphic to a Hilbert direct sum of finite dimensional irreducible co-representations. And the proof is exactly the same as in the case of compact groups. So first of all, we start with, we take an arbitrary invariant subspace of the smallest possible dimension, and we apply the same argument to the orthogonal complement. So after finitely many steps, we get a decomposition of our space into finitely many irreducible subspaces. So this resembles classical theorem from the representation theory of compact groups. Finally, there is a very useful collection of results, which are called the Tonnage theory. Roughly, the results are as follows. First of all, we can construct a very useful Hopf subalgebra in our compact quantum group, which consists of matrix elements of finite dimensional co-representations. This Hopf subalgebra is dense in our compact quantum group, and the density is not entirely obvious, and it follows from a quantum version of the Peter-Weil theorem. And actually, this Hopf star subalgebra remembers all information about co-representations of our compact quantum group. So the Tonnage duality theorem enables us to reconstruct this dense Hopf subalgebra from the category of finite dimensional unitary representations of or unitary co-representations of our compact quantum group. And moreover, there is a closely related result which describes all such categories, I mean categories of finite dimensional co-representations of compact quantum groups in abstract terms. So such categories, they are called, so they are monoidal C-star categories satisfying some extra properties. And such categories can be interpreted as dual objects to compact quantum groups. But this is quite a long story. So if we are interested in the details, you can find them in a very nice book by Sergei Nishveyev and Lars Tusset. The title of the book is Compact Quantum Groups and Their Representation Categories. Okay, thank you. So this is the end of our course.